So now I'd like to get into what is maybe one of my favorite chapters, and that is chapter number 8. This is all about bonding. Now, this first figure right here, this picture right here, shows you a couple of different things. One, it compares and contrasts the material. So this spoon is a metallic substance compared to this powder right here, which is an ionic compound. And then the water in which, or the solution, the solvent in which you're about to drop this ionic solution into, or this ionic substance into. This chapter is great just because I think that it really gets to show you like what individual molecules look like, as well as what individual atoms look like. So the first thing that we're going to get into is our definitions of our types of bonds. There are two major categories of bonds. There are ionic bonds and there are covalent bonds. Okay, so the difference between these is basically the presence or what all of the individual atoms involved in this bond or these bonds are doing with their designated electrons. So if we look at an ionic bond, what we're dealing with a transfer of electrons. So one atom will give up some electrons to another atom, in which case what we're doing is we're having a pair of ions form, basically. Okay, compare that to a covalent bond in which there's an equal sharing of electrons between individual atoms. So atom A versus atom B, well, they each have they can each lay a claim to any sort of electrons that are making up that bond. Now, in terms of the composition of different substances, well, if you're talking about something that has an ionic bond, you're talking about it having a metal or being made up of a metal and a nonmetal. If you are kind of in contrast talking about a covalent substance, you're talking about a pair of nonmetals sharing electrons between them. All right. Now, to go into our bonding types a little bit further, there are nonpolar covalent bonds and there are polar covalent bonds. So remember, a covalent bond is a bond in which two atoms are sharing electrons between them. Now, a nonpolar covalent bond, each of these two atoms kind of have an equal claim to those electrons. So if you wanted to look at it as nucleus of atom A and atom B, well, these electrons, and I'm just going to show kind of electrons are evenly shared between these two atoms compared to, and I wrote letter E there, so a polar covalent bond would look a little bit more something like this, where we have the electrons that make up that bond that are closer to one of those given atoms. So that would be an example of an uneven sharing of electrons between two atoms. Now, a metallic bond is a little bit more complicated than that, but think about that as more or less, or it's kind of characterized very simply as a sea of electrons. All right, now to dig deeper into ionic bonding. Ionic bonding results from an electrostatic attraction between a positive metal and a negative nonmetal. The ions are formed from the transfer of one or more electrons. And so this is actually, we've talked about ionic compounds, but we haven't really talked about ionic bonds. Now, in general, and I'm trying to think of a little bit of an outlier to this, but in general, metal is going to lose electrons to form a cation, and a nonmetal is going to gain electrons to form an anion. We've already talked about this. For instance, lithium generally is going to become oxidized, there to use a little bit of terminology. It's going to give up an electron and form an Li plus cation, whereas something like chlorine is going to gain an electron to form a Cl minus chloride anion. So if you think about these two things kind of going together with one another, lithium in the presence of chlorine, well, lithium is going to give up an electron, and chlorine would gladly accept that electron to form that chloride anion. Now, drawing a Lewis dot structure is maybe one of my favorite parts of General Chemistry 1 because I feel like it just opens the door to so much beyond this. So this is something that you'll talk about in organic chemistry as well as any upper division chemistry class. And whenever you're doing any sort of Lewis structure, the electrons that you're actually concerned with are the valence electrons. You're not concerned with all of those electrons because if you think about something like francium, well, francium has tons and tons of electrons. I can't really remember right off the top of my head, but a very large number of electrons. The only electrons that are going to be involved in drawing a Lewis structure are those valence electrons, and you're going to show those as dots. This utilizes what is known as the octet rule, which is basically summarized as atoms tend to gain, lose, or share electrons and then until they are surrounded by 8 valence electrons. There are, however, some exceptions. Hydrogen is kind of always an exception because it only wants 2 electrons around it, but then there are other exceptions like boron, for instance. Another exception is your noble gases. Noble gases, those are able to exist as individual atoms. They don't have to give up or gain any electrons, and they are good to go. Now, we're able to see our valence electrons here. I'm going to go ahead and highlight those valence electron numbers. Here, 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 and here. But to draw a Lewis structure, I'm going to go ahead and draw the Lewis structure for, let's go with neon. Neon is Ne. That wants 8 electrons around it. Ne, the Lewis structure for that is 2, 4, 6, 8. It does not have to be involved in any sort of sharing of electrons or anything like that. Fluorine, well, fluorine is 1, 2, 3, 4, 5, 6, 7. 7 electrons around it. Whenever you compare that with fluoride, well, that's F minus. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. That's a fluoride anion that has 8 electrons around it. So it's in great shape. All right, well, I hope this was helpful. Have a good afternoon.